The heavenly visitor has made some meaningful difference, as stargazers have found our sun-powered framework was once visited by an unfamiliar star that fundamentally changed the directions of certain comets and ice lumps. And albeit the upsetting star had an incredibly low mass, it was still enough to work up the items in the Oort cloud. However, what prompted the shimmering gatecrasher to enter our nearby planetary group in the first place? Where is the star today? Also, what lessons could we learn from this astronomical experience? Discuss seemingly perpetual, albeit the launch of the 2 Voyager tests now goes back over 45 years. The shuttles have proceeded undaunted on their journey through the immense territory of space as the most remote stations of mankind. The indistinguishable sister tests have now even wandered into interstellar space, and they have put billions of kilometers between themselves and the Sun. Voyager 1 is right now an incredible 16,466 astronomical units, AU, away from our host star, and with the knowledge that an astronomical unit relates to the mean distance between the Sun and the Earth, approximately 150 million kilometers, we understand that this is about 2,463 billion kilometers. Voyager 2, on the other hand, is even closer to the Sun. After all, the distance between the test and our brilliant life-giver is a mere 13,761 Australian dollars, or 20.59 billion kilometers. However, if you gazed up at the night sky around 70,000 years ago, you wouldn't see the Voyager tests, but you could see a striking red speck in the atmosphere. This was not because there was no light pollution in those days and the brilliant sky looked substantially more glorious than it does today, but because of a heavenly visitor that had slipped into our solar system. Rigorously speaking, the star visit even arrived in a double pack. We are dealing with a red dwarf which is likely joined by a brown dwarf. This was given the cumbersome scientific name, WISE J07200 3.20-08465 and is generally also called Schultz's star. Unexpectedly, the star system owes its less-than-weighty name to its discoverer, Ralph D. Schultz, who was the first to identify the objects in 2013. Since red dwarfs are known to experience savage ejections from time to time, our predecessors and the Neanderthals might have wondered about a ruddy mark of light overhead millennia ago. Anyway, the reality that the diminutive star truly merits its name, in spite of all its radiant exhibitions, turns out to be clear when we consider its combined mass of just 0.15 solar masses. Subsequently, specialists at first thought it incredibly improbable that the heavenly lightweight would have a huge effect on the celestial bodies of the planetary system. However, at the same time, there were also various irregularities that made the scientists dubious. While Schultz's star is now around 22 light-years away from Earth, it seems to be scarcely moving despite this somewhat close proximity to us. Essentially, there are 2 different ways to explain such a supposedly small tangential movement. Either the star is just going to head towards a nearby planetary group, or it is getting away from it. To figure out which case applies, researchers at the University of Rochester investigated the star's trajectory using spectral examinations, and an amazing miracle occurred. The assessments of the measurements clearly demonstrated that Schultz's star is now on its goodbye visit through the planetary group. On the other hand, however, this also meant that in the past it must have been much closer to the Sun. But how close precisely? Well, to find the answer to this question, cosmologists fed a model with the star's trajectory data and speed and essentially returned to some time in the past. Toward the end of this virtual journey through time, the result was that 70,000 years ago, Schultz's star went straight through the Oort cloud in 98% of the 10,000 different orbital reenactments. To briefly recap, the Oort cloud is a speculative shell-shaped region in the peripheral ranges of the planetary system that is believed to be the origin of long-period comets. And even though its presence has not been proven, specialists expect the Oort cloud to extend up to 100,000 Australian dollars. Anyway, since Schultz's star has a very little mass, as mentioned, the specialists at first expected that it didn't cause any significant disturbances during its entry through the distant collection of ice and rock fragments. Well, they could have been wrong, but more on that in a moment. There was also something that the specialists recognized right from the beginning. There could be no other known star that has ever come as close to our solar system as this one. In cosmic terms, however, the word close still means 52,000 Australian dollars, or 0.8 light years. But the star now nearest to the Sun, Proxima Centauri, is situated at 4 light years, an entire multiple times further away from our central star. Here is your text, punctuated for clarity and readability. Start a galactic difference in heart. In spite of the low masses, the hypothesis that the directions of extensive stretch comets were once fundamentally impacted by close heavenly entries is not new. It's only that, for quite a while, there was no known delegate that would have met the galactic necessities for it. Anyway, it ought to be noted right now that not all scientists were persuaded by the thought that the visit of Schultz's star had no impact at all on its environmental factors. Among these skeptics, as we presently know, were Carlos de la Fuente Marcos from the Complutense College of Madrid. Therefore, he and his partners assessed the circles of nearly 340 items that pursued through the planetary group on incredibly unbalanced ways exhaustively. The specialists not set in stone in their reproductions the bearings from which these exaggerated protests clearly come, and fundamentally, it would have been normal that their positions would be equitably conveyed across the sky. After all, the Oort cloud encompasses the inside of the solar framework, like a shut shell. Yet, contrary to all past suppositions, reality laid out something else entirely. The specialists recorded a measurably huge grouping in a specific course. According to this, the greater part of the inspected lumps depict direction that points toward the path of the group of stars Gemini, which implies that the beginning of the items lies in exactly that locale of the Oort cloud that Schultz's star was nearest to a long time back. As indicated by the stargazers, it is far-fetched to say the least that this is an incident. Rather, there should be a reason for the system's orbital arrangements, to be specific the Rock AG star section. After all, the area and season of these orbital aggravations match Schultz's star well to the point that they in a real sense shout for an immediate association. Also, on the off chance that you follow the analyst's estimations, the heavenly body might even have drawn somewhat nearer to the Sun than at first suspected. The comparing distance might have been not 0.8, but 0.6 light years. At this decreased distance, it should have in a real sense slung a few ice lumps out of their unique circles. But what does the circumstance really seem to be today? Well, as noticed, Schultz's star has now moved back to within 22 light years of the Sun. Furthermore, it will probably be some time before the next star emulates its example. On a basic level, specialists expect that a star will move toward the Sun to within 52,000 Australian dollars, or less somewhere around once every 9 million years. But there is a star that is now in somewhat of a hustle, the star that is jumping towards the solar framework. A mood that not everyone wants to follow. While most stars move as a whole around the center of the Milky Way, there are also exceptions known as rebel stars that don't really like the all-encompassing cosmic beat. One of these rebel stars goes by the name GLE 710, and it's presently on a crash course with our local planetary group. Rather than Schultz's star, in this case, the specialists concur from the beginning that the heavenly visitor will cause a lot of confusion in the Oort cloud. This is because, while the 0.6 solar mass star is presently still 62 light years from the Sun in around 1.3 million years, it's supposed to have drawn closer to the Sun to within 1.1 light years. In this unique circumstance, anyway, it's also thought of swirling up the items in the Oort cloud so much that an out-and-out comet shower will enter the inner local planetary group. This also increases the risk for Earth of being hit by one of the released cosmic shots. In this regard, scientists believe that the frequency of comet impacts on Earth will increase by no less than 5%. For our far-off relatives, we might dare to hope that not even one of them is a gigantic rock with the potential to annihilate the whole planet. On the other hand, there are still a couple of days left until 1.3 million years from now, and NASA has already demonstrated with its DART mission how the direction of a heavenly body can be changed with a designated effect. And now we'll show you how you can alter the recordings on your landing page by tapping the subscribe button. Press approval and click subscribe. Never miss another post from us again. We'll see you soon.